This module is going to be about the central limit theorem, which is arguably one of the most important theorems in probability theory. Some would say it's the most important, and let me tell you why. You've seen surveys done, and you've seen that as a consequence of that, there's always some kind of a bell-shaped curve. Now, the underlying population may not have a Gaussian distribution at all. However, if you take samples and you take more and more people or objects or whatever, then you will see that the histogram that is made then approaches that of a bell-shaped curve. Why does this happen? We'll be able to show using various different examples that this happens for almost any probability distribution. And we'll be able to use good mathematics to prove that this is a solid result. But first, let me explain to you how, in fact, we use the central limit theorem when people do statistics. For example, with potatoes. Instead of stating the central limit theorem at the very outset, what I will do is use potatoes as an example. Obviously, if there's a truck full of potatoes, we cannot examine each one of those potatoes, but we can take a sample. Let's call that sample size n, small n. In this particular case, I've taken n equal to 10 potatoes. Each one of the potatoes that you picked up can be weighed, and then you record the weight. For this sample, so sample number 1, I equals 1 means that you simply add up all the weights of the potatoes and you divide by n. So that's the average weight of the potato in the first sample. Then you must throw all the n potatoes that you took out of the truck back into the truck randomly. Why is that necessary? Because otherwise you will have altered, you will have tampered with the distribution. Then take more random samples, do the second sample, the third sample, and the nth sample, and here this is a capital N. We can, of course, make n large. Thereafter, you can make a histogram of the averages. This is what is called the sampling distribution for sample size n. So, over here, the first sample that you took, the average weight of potatoes was this, the second was this, and so forth. Here's the seventh. Now, this does not look very much like a Gaussian, but that's because we took only 10 potatoes. What we will see later, and this will be quite astonishing, that this, which does not look like a Gaussian very much, will in fact look something like this Gaussian. Of course, I've not drawn it very well. To make the idea of a sampling distribution clearer, let me take a total population of just 4 potatoes. So, the total population n is the entire population, and I will take just 2 potatoes randomly. That will be my sample size. I'll use this notation, the weight of the first potato, of the second potato, and their average weight. I will take the first potato, close my eyes, put it back, pick up the second potato. Of course, I could get back the first potato, in which case the average weight will simply be 150, but I could pick up the second potato or the third or the fourth, and the average weights will be what you have in front of you, 165, 155, 160. Then let's look at the other possibilities. So I could have picked up the second potato, in which case this would be 180, and then the next potato that I pick up could be 150, 180, 160, or 170, and these would be the average weights over there. Similarly, I could have picked up the third potato, in which case I would have got, again, these averages here and here, in which case I'll get these over here. So now you see that I can get only 6 values for the average. 150, 155, 160, 165, 170, 175, and 180. Here's a table that summarizes what we've learnt. This is the average weight for a sample size of 2. The probability that I will get 150 as the average weight will be 1/16. Why? Because there's only one way in which I can get 150, that is, if the first and the second are both 150. On the other hand, I can get 155 in 2 different ways. That's because I have this possibility as well as this possibility. Similarly, 160 has 3 possibilities, 165 has 4 possibilities, and so forth. And 180 is possible only when the first potato and the second potato are both 180 grams. We can make a bar chart of the probabilities. So this is the probability 1/16, 2/16, 3/16, 4/16. And now you see that this is like sort of a Gaussian over here. But we're not going to take that seriously at this point. Now let's think of the average sample weight as being a random variable. Let's call it W. Well, that random variable can take these different values over here with these different probabilities. And so, as we know very well, we can take an average by taking the value of that random variable weighted by the probability. And in this case, if you do a simple calculation, well, 150 multiplied by 116, 155 by 216, 160 by 316, and so forth, you add them all up, you get 165, which is the average value of the random variable W. The average value of the random variable W squared is going to be just the same, except that instead of W bar, we have W bar squared. And so what we have is simply, instead of 150, 150 squared. Well, keep adding them up. It's a fairly large number. We don't really need it. What I do want to emphasize is that this way we can get the standard deviation of W, which is the square root of the random variable W bar squared minus the average squared. And so if you do a little bit of calculation, that's simply 5 into square root of 5 over 2. Remember, this is for the case where we take only 2 potatoes randomly out of the total population of 4. But now, let's ask, what if we had taken n equal to 1? That is to say, if we had taken 1 potato at a time. In that case, it's pretty trivial that the probability of picking any one of these up is 1/4, 1/4, 1/4, 1/4. And so if you make a histogram, of course, they're all the same height, 1/4 each. If you take the average weight of the potatoes, well, then it's 150 times 1/4, 180 times 1/4, 160 times 1/4, 170 times 1/4, and that's 165, which is exactly what we had before. However, if we now look at the average of the square of W, then we put 150 squared over here instead of 150, 180 squared instead of 180 here, and weight them with the probabilities 1/4, 1/4, etc. Do a little bit of calculation, and we find that the standard deviation is 5 times square root of 5. Compare this with the result that we just got for taking a sample size of 2. So what we found is that the result is the standard deviation for the population multiplied by 1 over square root of n. The reason for this 1 over square root 2 is going to come from the central limit theorem, but that's for later. The central limit theorem is actually quite astonishing. You can have very different distributions of the population. Something that looks like this. 0 here, a constant here, 0 again. Or it can be wavy looking like this, or it can have a bump in the middle and then go off to 0 over here. As long as it is reasonably well behaved, it says that for any population which has an average and a standard deviation, and of course all of them do, or most of them do, then if you look at many random samples, then the sampling distribution, now this is very important, the sampling distribution will approach a Gaussian or a normal distribution in the limit where the sampling size n becomes larger and larger. Or to say it slightly differently, if you take samples from this distribution or this distribution or this distribution, then as long as you make your samples large enough, you're going to get this bell-shaped curve. Now this is something that is still to be proved and still to be fully understood, but we'll do that in the next few minutes. Before we get into the central limit theorem and learn how to prove it and then apply it, let me emphasize a few key features. First of all, generally speaking, the population n is large. So for example, this could be a population of a country which has many millions, but suppose we want to look at the heights of people in that population. Well, we're not going to take the whole population, we're going to take samples, and those samples are generally small. Now, how small is small? That is something that experience will tell you, but something like 30 is what is generally used by statisticians. However, the bigger you make this, the closer you will get to getting a Gaussian or a bell-shaped distribution. Now, when you take a sample, that sampling should be relevant and it should be without bias. So, for example, if you're looking at the distribution of potatoes in a truck, then you shouldn't just look for large potatoes or for small potatoes, because that would be bias. Furthermore, the sampling should be relevant, which means that you should be looking just in that truck, not some other truck which is parked nearby. Then, some sample units may be those selected earlier. So, as I emphasized earlier, once you take a sample of potatoes and you weigh them, then you must throw them back into the truck, because otherwise you will have changed the distribution, and so the second or the third or the fourth sample that you take will be biased. Replacement is therefore necessary. And of course, the average of the sample means approaches the population mean as you take more and more samples, or as the sample size becomes larger. And this would follow from the law of large numbers that we covered in the last lecture. Before we prove the central limit theorem, let me remind you of the moment-generating function of the normal distribution. So here is the normal Gaussian distribution. Its mathematical form is the exponential e to the power minus x minus mu squared divided by 2 sigma squared, and this factor over here ensures that the integral of the Gaussian is equal to 1. We shorten this, we write this as p of x, and the interpretation is that the probability of finding x between x and x plus dx, that is to say in this small range of x, is equal to p of x into the width dx. Now, when the Gaussian is written in this form, it's a little bit too complicated because you see that this has a maximum when x is equal to mu. That's because we have e to the power 0, which is 1. And then it falls off as you move to values bigger than mu or to values less than mu. As a step towards simplification, it's going to be very useful to define a new variable, z, which is x minus mu divided by sigma. Obviously, this is so because if I take the square of this, well, that is exactly what we have over here except for this 2. And so this is the factor. The exponential factor is just e to the minus z squared over 2. However, you see over here that we have dx. And now dx is equal to sigma dz. And so that sigma and the sigma over here, remember this is sigma squared under the square root, so that's sigma. So those sigmas cancel, and so we get dp as equal to this thing times dz. And that, you will agree, is quite a bit simpler than what we have over here. So now let's look at the Gaussian in this form and ask, what is the moment generating function of this Gaussian here? As always, we take e to the power tz, take the probability distribution function, integrate over all values of z, and that is, of course, simply this, e to the tz, e to the minus z squared over 2. As you can see, this thing over here is the same as e to the minus half z minus t squared, and there's e to the half t squared outside of the integration sign because this does not depend upon z. Now, this integral over here is simply square root of 2 pi, and so we get e to the t squared over 2. That is the moment generating function of the normal distribution. This is going to be crucial in our derivation of the central limit theorem. Let's now move to the case where we have n identical, independent random variables. Let's first take a single random variable. For that single variable, the moment generating function, as we've discussed many times, is this thing, e to the tx times the probability distribution function for that random variable, and then you integrate over all values of x from minus infinity to plus infinity. If you were doing this for a discrete random variables, all you would do is replace the integration by a summation. Obviously, if you put t equal to 0, then you get 1. If you want the average value of the random variable x, then you weight the probability distribution with the value x and integrate over all values of x. That's exactly what you would get by differentiating with respect to t, this function here, and then setting t equal to 0. And in general, of course, you would get the nth moment by differentiating n times. We've covered all this here before. I'm just putting it here to remind you. Now, what if we have not one variable, but n variables? So, in that case, the probability distribution function would depend upon n random variables, x1 up till xn. And then, if you want the moment generating function, well, you multiply by e to the power t, x1 plus x2 all the way up till xn. There's a single parameter t upon which this depends. Clearly, if you put t equal to 0, then you're integrating over all possibilities, and you would get simply 1. If you differentiate this quantity and then put t equal to 0, then you will get the average value of x1 plus x2 plus all the way up till xn. And now this is weighted by the joint probability distribution of n random variables, which of course you would write as this, average of x1 plus x2 all the way up till xn. This so far is completely general. However, if you have independent, identically distributed random variables, that means that this p over here, which depends upon n variables, actually is simply a product of n p's. And since they are identical, therefore they're all the same. All the p's are the same. However, their arguments are different. x1 here, x2 here, xn here. This is the statement of independence. In that case, the moment-generating function then takes this form. And of course, we have to do this integration with n variables. However, now you see that this simplifies because e to the power t into x1 plus x2 plus up till xn is the product e to the power tx1 times e to the tx2 times e to the tx3, etc. And so this n-dimensional integration is simply a product of n one-dimensional integrals. So this is a one-dimensional integral, and so are all the other ones, including this one over here. Since all of these integrals are exactly the same, remember that this x1 here is just a dummy variable, and so what we have is simply one integral raised to the nth power. And that comes about because the joint probability distribution is a product of n distributions which are identical. We are now very close to proving the central limit theorem, and our goal will be to show that the function for generating moments is exactly that for the Gaussian distribution. So let's begin by defining this moment distribution, m of t, and it's just what you had before, e to the power tx, except that now, of course, we have n variables, and we're going to use just the right coordinates. So the distance of x1 from mu, and similarly of all the x's from the common mean value, mu, and then, of course, with this factor over here, the standard distribution, square root of n. Now you'll say, why did I take this particular variable? Well, nothing is to stop me because there's a definition over here. So m of t is defined as this, and this is true for any probability distribution function that depends upon n variables, x1 up till xn. Well, of course, we are interested only in independent, identically distributed variables, and so, as before, we're going to write what's over here as this product over here. And this expresses both the fact that the random variables are independent and they are identical. Okay, so now let's proceed and use what we had before. Earlier, we had m with just e to the tx over here. But now we've learned something, and we are going to use this exponential here, weighted by the same p of x, and raised to the nth power, where n is the number of independent random variables. I remind you now that we can always write any number to the power c, so b to the power c, as e to the c log b. Very, very useful. And you know how to check this? Just take the log of this side, the log of this side, they're both equal. So if we use this, we get this thing over here is equal to the exponential of n log times this integral over here. So this is p of x multiplied by this exponential, but the exponential has a 1 over square root of n in the argument, and so as n becomes bigger and bigger, this argument is going to get smaller and smaller, which means that we can sensibly then expand this out. And let's do that. So the first term is 1, then the second term, when you expand out e to the x, is x itself. This term after that is 1 over 2 x squared, and so that's that term over here. And now let's look at each one of these terms separately. 1 gets multiplied by p of x dx. Once you integrate over all x, you get 1. That's because of the normalization of this function over here, this probability distribution function. What about the second term? Well, x gets multiplied by p of x and integrated over x. That gives us the average value of x, which is mu itself. And so this term over here goes to 0. This does not occur anymore. What about here? Well, here we have x minus mu squared, and mu is the average value of x, multiplied by p of x. What is this? Obviously nothing other than sigma squared itself, the variance of x. And so this times p of x integrated over x is sigma squared, which will cancel this sigma squared over here. So the next step is we have the exponential n log of 1 plus 0, this 0 from here, and over here nothing other than t squared over 2n. At this point, we will use the fact that log of 1 plus epsilon is approximately epsilon. The next term is minus half epsilon squared, but we won't need it. And so now we have the exponential of n log times this. Well, now use what we have just discussed, and that's e to the t squared over 2, and that's a great victory. That is the generating function for a Gaussian, and so we have achieved victory. This is the proof of the central limit theorem. So, as n becomes larger and larger, m of t has become the moment generating function for what we had called Zn. And Zn is just the sum of the random variables x1 up till xn minus the average value, which is n times the average value for one single variable. And the way that we defined it was we then divided by sigma times square root of n. That is actually what was put in by hand by us above. And so another way of writing this is Sn divided by n minus mu. So all I've done is I've divided this side over here by n, and here is what we get, with Sn being the sum of the random variables x1 through xn. Finally, we have a very clear understanding of what the central limit theorem is all about. And now, to understand this better, we will take a few examples. What we've just proved is the central limit theorem for identical, independently distributed random variables. However, we didn't say what those p of x's were. Now I'm going to take a particular example, which is that p of x is this thing over here. It's 0 when x exceeds 1. It's 0 when x is negative. It's 1 if x is between 0 and 1. And so, of course, you can picture it as this. And, of course, the area under this curve is 1. So the 0th moment is 1. What about the first moment, which we have called mu? Well, mu is equal to just x dx from 0 to 1 itself, and that's a half. If we take the second moment, well, that's x minus mu squared times p of x, but p of x is 1 if you're between 0 and 1 and 0 elsewhere, and so it's just this simple integral over here, which is simply 1/12. And so now we can define our Zn, that variable which we had used in proving the central limit theorem. And that Zn is just the sum of the random variables, what we called Sn over here, divided by n minus mu, and the whole thing divided by the standard deviation over square root of n. N is something that we are allowed to vary, and we can therefore begin with n equal to 1. So let's start with that. In that case, from here, we're going to have z1, which I'm going to call z. So z is equal to 1 over 1. There's going to be an x minus mu. Mu is a half. Then divided by sigma. Sigma is 1 over square root of 12. And so we have this new variable. Z is square root of 12 into x minus mu. I haven't called it half, but of course, from here, it is that. Next, we're going to write dz as square root of 12 dx. Now let's recall the meaning of a probability distribution function. P of x times dx is the probability that x will be found between x and x plus dx. We'll give that a name, we'll call that dp. Now I'm going to change variables from x to z, and that simply means that instead of expressing p as a function of x, I'm going to express it as a function of z. Instead of dx, I'm going to write dz, and of course the relationship is over here. And so this is now to be interpreted as the probability of finding z between z and z plus dz. The next step, instead of writing p of x in this way, we're going to write p of z. Now p of z will be this thing, 1 over square root of 12 p of this variable over here. So you can see from here that x will be z divided by square root of 12 plus mu. Mu is a half. And so p is the same as before, but this time expressed in terms of the variable z, and I have used dx is equal to 1 over square root of 12 times dz. So what does p as a function of z look like graphically? You can see that z equal to minus square root 3 corresponds to x equals 0, and what corresponds to x equals 1 is z equal to plus square root of 3. These statements, of course, come from here. Now, what we have is p as a function of z. You can see that this shaded area over here is equal to 1. That's because this height from here to here is 1 over square root of 12, whereas this width is 2 times square root of 3. Multiply the two and you get this 1 here. You can also calculate the average value of z, which is 0, and that's very, very obvious. This curve is symmetric, so for positive z or for negative z, the value of p of z is the same. If you calculate the standard deviation, well, that's sigma 1 equals 1. This 1 over here means n equals 1. Now for n equal to 1, this doesn't look very much like a Gaussian at all. Should we therefore go to n equal to 2? Let's do that. Now what I have is n equal to 2 here. So z2 will be x1 plus x2 minus 2 into mu. Mu is a half, so minus 1. That's why we have this x1 plus x2 minus 1. And then, of course, there's going to be square root of 2 times sigma, and sigma is 1 over square root of 12. So therefore, this is the appropriate definition of z for two identical independent random variables. Again, we'll define the probability distribution P as the following. The probability of finding x1 in the interval dx1 and the probability of finding x2 in the interval dx2 is this thing over here, which, because the two random variables are independent, is of course just the product that's over here. Now you see I have actually two independent random variables, whereas if you look over here, there are three. There's z, there's x1, and there's x2. Well, that means that there are only two independent variables, and so we have a choice as to which to call independent. The third one will be dependent. So I'm going to choose x1 and z as the independent variables, in which case x2 from here is then dependent. It's just this, 1 over square root of 6z plus 1 minus x1. So then, having chosen z and x1 as the independent variables, I can write dx2 as simply this, 1 over square root of 6 dz. Of course, more properly, I should have a Jacobian over here, but the value of the Jacobian is 1 over square root of 6. Now, just as we did before for n equal to 1, we're simply going to write p of x1, x2, but now express x2 in terms of the two independent variables, z and x1. And of course, there's dx1. No longer is there dx2 over here. We've replaced dx2 by 1 over square root of 6 dz, which from here can be written as p of x1 times p of this new variable, which is x2, expressed in terms of z and x1. Let's now integrate over all values of x1 from minus infinity to plus infinity, the whole range of x1. We have to do this integral over here if we want p just as a function of z. Okay, now this p of x1 we know very well. This is 1 if x1 is between 0 and 1 and it's 0 otherwise. So we're just going to replace this over here with a 1. And now the integration on x1 goes from 0 to 1. But it's not completely straightforward, because now we've got to have p as a function of x1, but there's z coming in over here. So this is a nice, interesting integral now. How will we deal with it? Well, I'm going to define a new variable. I'm going to change variables to u. This u is what occurs inside over here, 1 over square root of 6z plus 1 minus x1. Now we are holding z fixed. Remember that z is occurring over here. We are not integrating over it. So dx1 is the same as minus du. And so this integral over here becomes simply p of u du. I've taken this 1 over square root of 6 outside over here, so there's nothing to do over there. But now look at the limits of integration of u. When x1 is equal to 1, then u becomes 1 over square root of 6z. When x1 is equal to 0, then u becomes 1 over square root of 6z plus 1. So that's what you have over here and over here. And of course, the minus sign gets switched around when you interchange the limits over here. There's only a little bit more work that you have to do. For values of z that lie between 0 and square root of 6, then p of z becomes this integral, from here to 1. And this is a trivial integral to do. it's simply equal to this, 1 over square root of 6 minus z over 6. On the other hand, I can take z being between 0 and minus square root of 6, in which case I get p of z equal to this. Now note that this is a straight line in z with a slope minus 1 over 6, and this is a straight line in z with a slope plus 1 over 6. P of z is certainly continuous at z equal to 0 because its value over there is 1 over square root of 6, both from here and from here. Now let's sketch it. What we see is that P of z is this function. It's 0 up till here. It becomes 1 over square root 6 here, goes back to 0 over here. And wait, although this is not Gaussian looking, but it's closer to a Gaussian than the flat one we just saw a little while ago. Again, the average value of z is 0. This is a function that's the same here as it is over here. Further, the standard deviation is like before, 1. Earlier we had sigma of 1 equal to 1. Now we have sigma of 2 equal to 1. So we've done n equal to 1. We just did n equal to 2. What about n equal to 3? It's a little more complicated, and it took me quite a while to figure out what p of z is. It's only a little more complicated, but let's review what we've done so far. So this is a new variable, zn, to be called z in this case, and this case. We have x1 plus all the way up till xn minus mu times n, and when we took n equal to 1, we got p of z as being this. When we took n equal to 2, we got this thing over here. But when we take n equal to 3, then we get something much smoother. Actually, this is a nice calculation to do. Here, you will have to integrate over 2 variables. Here we had to integrate over 1 variable. Here we had to do no integration at all. So what is it that we've proved? That from something that is as flat as this, something that does not look like a Gaussian at all, as you go to larger and larger values of n, you get closer and closer to a Gaussian, and if you take n large enough, then you get to a Gaussian, just as we proved for the central limit theorem. In the previous lecture, we had talked about how the binomial distribution converges to the normal distribution and how you get a Gaussian from that. Well, here I'm going to return to that, taking the example of a die. So this die over here has a probability of 1/6 for landing on any face. That means P is equal to 1/6, Q is equal to 5/6, and sigma is equal to the square root of P into Q, which is 5 over 36. Now if we throw this die once, then there's equal probability of getting 1, 2, 3, 4, 5, 6, because there's just one way in which you can get any of these numbers. So that's the probability over here. But now let's take 2 random variables, x1 and x2, add them together. You can get at a minimum 2. So if both die land with a 1, then that adds up to 2. If both land with a 6, that adds up to 12. If you look at 3, well, 3 can be done as 1 plus 2 or 2 plus 1. And similarly, we can go through all these different combinations over here. Now you're beginning to see that there's something that's sort of looking like a Gaussian, but not very much. However, if you go to n equal to 3, it becomes nicer. To n equal to 4, still nicer. And you see that at this end you have 4. That's because n is equal to 4. You've thrown the die 4 times. And if they all land with a 6, then you get a maximum of 24. The most probable sum is 14. And now it's perfectly obvious that this is now looking even a better Gaussian. And now reflect on the fact that although I had shown in the previous lecture that as n goes to infinity, the average values approach a Gaussian distribution. But here you don't have to go very far in n. Just n equal to 5 is good enough for the binomial distribution. Let's now apply the central limit theorem to buying potatoes. So, suppose the average weight of a potato in a certain farm's potato population has the average equal to 200 grams, and there's a standard deviation, so some potatoes are heavier, some are lighter, and that standard deviation is 50 grams. Suppose a customer purchases 100 potatoes. What is the chance that she will have purchased potatoes weighing between 19 kilograms and 21 kilograms? So now we are talking about n equal to 100 and the total weight of 100 potatoes. Well, the solution is as follows. This will be normally distributed as a Gaussian, and the probability of finding z in this interval dz, from z to z plus dz, is, as we've discussed, p of z dz, where p of z is this Gaussian, and we have defined the variable z as before, the sum of all the x's from x1 up till x100, so that is the total weight of the potatoes, minus the average, so n into mu, and then we divide, of course, by the standard deviation sigma and square root of n. We expect, as before, that as n becomes large, we approach a normal distribution. And now let's see. For n equal to 100, the smallest value of z will be, this s will take the value 19 kilograms, and we have to subtract from this 100 into mu. 100 into 200 grams is 20 kilograms, and so the lower value of z will be 19 minus 20 divided by the standard deviation, which is 50 grams, and then there's a square root of 100. That works out to minus 2. Now notice one thing. Over here there is a weight, and here there is a weight also. So there's grams on top, and there's grams at the bottom, and of course n does not have any dimensions. Anyway, that's minus 2. Let's look at the upper limit. So that is 21 kilograms. 21 minus 20 over 0.05 square root of 100 is 2. Okay, so what is the probability of finding z between minus 2 and plus 2? That, as we know from the meaning of probability distribution, is p of z dz integrated from the lower limit to the upper limit, which in this case is minus 2 to plus 2. And now you can either look this up in the tables or get your computer to do a numerical integration. So this p of z is then integrated from minus 2 to plus 2, and that works out to 0.9545. Actually, you've seen this number before. That's the probability of being between two standard deviations. Before concluding with this problem, let's ask, what is the probability of finding the weight between 19.5 kilograms and 21 kilograms? Well, in that case, just work out the lower value of z, which then is not minus 2. This becomes minus 1, so you integrate from minus 1 to plus 2. And if you just do this integral or look it up in a book, then this becomes 0.8186. Another application. Suppose that changing a car tire takes an average of 10 minutes with standard deviation of 2 minutes. So some tires are more difficult to open up than others, and of course the mechanic could be feeling differently and so forth. So It doesn't take 10 minutes always. It could take a little bit longer or a little bit shorter time. We are now asked to find the chance that it takes more than 7 hours to change 40 tires. Now 7 hours is 7 into 60, which is 420 minutes. Keep that in mind. Let's now think of the solution. So, the independent random variable in this case is the time xi needed to change a tire, for which the average time, the mean time, is 10 minutes and the standard deviation is 2 minutes. So, for 40 tires, we have 40 into 10, which is 400 minutes. Now, let the total time taken for changing 40 tires be the sum x1 up till x40, and we're going to call that t. Then, of course, just as we've derived for the central limit theorem, we have this new variable z, which is t minus n mu sigma square root of n, exactly the same as before for potatoes, except that here, instead of a weight, we have time. Remember, the question that we are asked is find the chance that it takes more than 7 hours to change so many tires. So this over here must correspond to 7 hours, and there's no limit to this, and so therefore this z2 will be infinity. Now let's put this in. So z1 is 7 hours times the number of minutes in an hour minus mu times n. N is 40, mu is 10, therefore this is 400. Just work this out, that's 1.581. And of course, z2 is infinity, as we just discussed. Again, we have to do a numerical integration, and so the probability that it takes time greater than 420 minutes is you integrate from that corresponding value of z, and this is an integral that any computer will do for you in a jiffy, and the answer is 0.057. In other words, there's a 5.7% chance that it'll take more than 7 hours to change 40 tires. Finally, let us apply the central limit theorem to voting. So, ahead of a referendum on a new tax law, an opinion poll is to be carried out. Suppose that an unknown proportion P of people are in favor of the law. In other words, the probability of finding a person who is in favor is P, and the probability of finding a person not in favor is therefore 1 minus P. We are asked the following question. A sample of n people is to be taken to find their opinion and to estimate P. How large should n be so that the estimate will always be correct to within 1%, with probability 95%? Now, of course, the more people you take, the more accurate will be your polling, but we are asked what is n, the minimum value of n, so that we can get this poll correctly to this accuracy with this probability. Okay, so then let's define the random variables xi in the following way. For I equal to 1 all the way up till n, xi is 1 if the ith person says he or she is in favor of the law, and it is 0 if that person says no. So then what we have is P is the probability of yes. The average value of xi is clearly P. We've done that many, many times. It's P times 1. And of course, xi squared average is also P times 1 squared, which is again P. And sigma squared then becomes P into Q. So that's P into 1 minus P. Now this over here, the variance or the standard deviation squared, is a measure of indefiniteness. Of course, if P is equal to 0, then no one is in favor of the new law, and if P is equal to 1, then everyone is in favor of the law. In that case, sigma will be 0. So now the question is, for which value of P is the uncertainty the greatest? In other words, when is sigma the largest? Actually, you can pretty much see the answer, because when P is 0, this is maximum. When P is 1, this is 0, and this is maximum. And so the maximum value of sigma squared, the maximum uncertainty, will lie somewhere in between. Let's see. The derivative of the function has to be 0, which means P is equal to half, and so sigma, which is square root of P into Q, that's square root of half into half, and that's a half. So now for applying the central limit theorem, we'll use this new variable, which is, as before, the sum of the random variables divided by n minus mu divided by this thing over here. And remember that the mean value is the same as the mean value for each of those random variables, and in this case, mu is P with P equal to a half. Well, again, we're looking for a deviation from the average value. So this is 1% less than half minus the average, and then divided by this sigma over square root of n, which is then minus 0.01 square root of n. The upper limit, in that case, 1% bigger than half, will be this much, minus the average, and that gives you plus 0.01 square root of n. Basically, we have this situation. So mu, which is half, is over here. We want to see what is the probability that z lies between here and here. So that's 2 standard deviations on each side. That's the 95% confidence level. Let's take the difference between this and this. Well, that's z upper minus z lower. That should be equal to 4 times sigma. Let's just put in their difference, which is 0.02 square root of n. And now that's 4 into sigma. Okay, so just simplify. And that says n has to be 10,000. So in the most unfavorable situation, you would need to take 10,000 different opinions. And that's because half the people would want the law and half would not. If we had some prior knowledge of the population, well then, this number could be much smaller.